Okay, folks, I show that it is that time. So I'm going to go ahead and get started. If I can get all this up and running. So as a reminder, you have a quiz that's due at 11:59 p.m. tonight. It is active and it is over what we went over on Wednesday of last week. So identifying the intermolecular force associated with a specific type of substance and identifying higher melting point, boiling point type information based on the identity of the substance. Your first official lab will occur this week. It will be a graphing lab. You will find that in your folder for this week. It will be under the laboratory materials. We will meet in class. We will do probably about, I expect to do about 4 of the graphs as a unit. So bring computer or something you can do some graphing with. And then we will, the last 2 graphs will be assigned to you to do on your own. And those are going to be what will be due the following Wednesday. You have a quiz 1 is due on Friday sometime, and I'm extending the deadline. I know I originally put noon, but I'll be here till 4:30 on Friday. So anytime on Friday will be fine after, other than from 8:30 to 10:30. I think it is. And then you'll have homework number 2 due on Sunday of next week, and it's going to be related to the material we're covering today and Wednesday. So those are the key items that I can come up with off the top of my head. Now, if you don't mind, please write your name on here, print your name. And again, thank you to those that have your thing up, but I did not bring the extras today because I barely made it back to campus in time to come to class. That's why I'm rushing around like a crazy lady, is I've been on campus a whole 10 minutes. So about 10 to 15. Okay. Any questions before I begin?
In the lab folder on Blackboard, I printed the lab and I already have it. I didn't see any pre-lab material.
There is no pre-lab material. There is no post-lab material. There is no quiz for this one.
Okay.
There is no math chem videos for this one on Edpuzzle. So this one, it's just come to lab. We're going to do graphing. And I know many of you have probably already been in a class that requires graphing. But I hear from many students the angst that they had because a lot of times it wasn't demonstrated the expectations. So that's what I will be doing is I will be doing 4 graphs and I will be demonstrating my expectations as I do those 4 graphs so that you know exactly what is expected of you throughout the semester when you're asked to graph data.
And the 2 that we're to do, you want us to print them out and bring them in and turn them in the second we walk into the next lab?
On Wednesday. Actually, it's before the next lab. It'll be the Wednesday before.
Yep.
But yes, you would print them out and turn them in on that Wednesday. Other questions? Yes. Labs will be turned in will be turned in person. Other questions? Okay, so if not, let's get started. So basically, just as a quick reminder of last Wednesday, We went over, give me my pen, thank you. We went over London dispersion forces. Every single molecule out there has London dispersion forces because London's dispersion forces are temporary dipoles that are caused due to the movement of electrons. And since everything out there has electrons, there is electron movement, and therefore we can expect London dispersion forces to occur. The second type we talked about was a dipole-dipole moment, or dipole-dipole forces. And if you'll recall, dipole forces exist in any molecule that is polar. And then finally, we talked about hydrogen bonding forces. And hydrogen bonding exists within polar molecules, but the polar molecules must contain a OH, NH, or FH bond. We then went on to talk about the strength of these. And we discussed that there's an increasing strength as you go from London dispersion to dipole-dipole to hydrogen bonding. Now, folks, I described it as a strength, but really what does that strength mean? That strength means how much energy must be put in order to separate two molecules of the same type. The stronger the intermolecular force, the more energy we're going to have to put in to pull those molecules apart. So that's what we mean by the strength, is how much energy do we need to put in to separate two molecules of the same substance. Now, we talked about the impact of those intermolecular forces. And basically, I described it using weaker intermolecular forces and stronger intermolecular forces. Basically, the weaker the intermolecular force that is present, the lower the melting point. The reason is, if you've got a weak intermolecular force, it's not going to take very much energy to separate those molecules, to go from solid into liquid. Whereas the stronger the intermolecular force, the higher the melting point. We said the same thing is true for the boiling point. The lower the boiling, or the weaker the intermolecular force, the lower the boiling point. Because again, it doesn't take as much energy to take a liquid and convert it into a gas, meaning that you've completely overcome all of the intermolecular forces. We've talked about it with respect to viscosity. Your substances with the lower intermolecular forces have a lower viscosity. Viscosity is flow, or resistance to flow specifically. If they have really weak intermolecular forces, there's no resistance to flow. Whereas if they have stronger intermolecular forces, you've got to basically break a force, make a force, break a force, make a force, break a force. So it takes a lot more to overcome them.
Does viscosity and density have anything to do with each other?
No, because viscosity is flow, whereas density is how many molecules are in a particular space at any given time. So they are different in that regard. We've talked about it with respect to capillary action. If you have weaker intermolecular forces, you're going to have less capillary action. Now, I didn't actually take much time to explain what capillary action was, because ideally you're watching the videos. But basically, capillary action occurs when a molecule drags along with it the next molecule, drags along with it the next molecule, and so on and so forth. So the stronger those intermolecular forces are that's between those molecules, the easier it's going to be to drag that molecule up with it. And so you would expect greater capillary action.
So is that like concentration gradients?
No, that's a completely different thing because concentration gradient, we're talking, when you talk about capillary action, you literally have a little tube and it depends upon it dragging the molecules, how fast that will rise up the tube. It also depends upon attraction. It's capillary action is nothing but attraction.
Okay, so would that be like, if you're like, in the case of-
Correct. Except it's not a, you don't actually have a sucking motion. I got it. To clarify, you've got a spill on the table, take a paper towel and just barely touch it to it. As the water rises up the paper towel, that's capillary action. So. And then there was also surface tension. The weaker the intermolecular force, the less surface tension we're going to observe. And again, it has to do with that strength. Then finally, the last thing I said that was kind of the oddball in this listing is the weaker the intermolecular force, the higher the vapor pressure. And vapor pressure is the pressure that the gas molecules above a liquid apply to the container that they're in. Vapor pressure is the pressure the gas molecules apply to the container they're in. So basically what you have when you have vapor pressure, which I was going to go into a little bit greater detail on, we have our liquid here. Now, what you have to think about with respect to this vapor pressure and this liquid, before we actually get into the vapor pressure, let's talk about intermolecular forces. If we think about it, well, I need another row. If we think about intermolecular forces, they are the forces between molecules. If you look at one of these top molecules, what it means is it's the attraction of one molecule to the molecule beside it, the attraction of that molecule to the other molecule beside it, and we can continue going and going and going. Basically, it's the intermolecular force is the attraction between that molecule and all of its surrounding molecules. Now, when you look at a molecule that's in the center, then what you have, thank you, is you have even greater numbers of attractions between those molecules, because there's greater numbers of molecules that surround it. So a molecule on the surface is going to have a lower set of intermolecular forces than the molecules that are in the center. Now, what happens is even at room temperature, some of these surface molecules can escape into the liquid layer above it. So you're going to have some gas molecules that are above the liquid line. Now, depending upon the intermolecular forces determines how many of those gas molecules are above the liquid line. If you have weak intermolecular forces, you're going to have a lot of gas molecules above the liquid line. If you have strong intermolecular forces, you're going to have fewer gas molecules above the liquid line. And it's these gas molecules that actually determine the vapor pressure, because what we're looking at when we actually talk about vapor pressure is we're talking about these molecules that are in gas form colliding with their container and applying pressure where they collide. And that is what we're referring to as vapor pressure. So the fewer molecules you have in the gas phase, the lower the vapor pressure, because you have fewer molecules interacting. So we said the stronger the intermolecular force, the fewer the molecules in vapor phase, and that's why you have lower vapor pressure. Of course, we can alter this. I mean, after all, we can add a flame or heat underneath this. And of course, we're going to increase the vapor pressure. So the vapor pressure is directly related to the temperature. And if you graph vapor pressure versus temperature, what you will see at the, I need to change that T. What you will see is that you will have fewer molecules at lower temperatures, but as you increase the temperatures, you're going to have greater numbers of molecules and therefore greater pressure. You have fewer molecules at the lower temperatures, but as you increase the temperature, you're going to increase the number of molecules going into the gas phase, so you'd have greater vapor pressure. One more time. You have fewer, at lower temperature, you're going to have fewer molecules in the vapor phase and therefore lower pressure. But as you increase the temperature, you're going to increase the number of molecules that go in the vapor phase, and therefore you're going to increase the pressure. Now I drew the 3 lines and said it 3 times, because when we think about our intermolecular forces, a lot of times when you have something that does hydrogen bonding, you're going to, wait, let's see. Nope, wrong thing, wrong direction. Lower temperature. Okay, so when you have London dispersion forces, they're going to go into vapor phase pretty quick. Whereas if you have hydrogen bonding, it's going to take a lot more energy to get those to go into the vapor phase. Now, this particular equation, if we were to get the equation, it would be pressure is equal to some constant, beta in this particular case, times E to the negative RT, or excuse me, delta H over RT. In other words, we have an exponential function when we're graphing. Just, and you can just leave it and I'll get it at the end. Now, exponential functions are great if you're just going to be determining bits and pieces, but they can be also a challenge. So we can take that equation with the exponential function. That looks terrible because that does not look like a exponential. And we can take that equation and we can take the log of both sides. So we can take the natural log of the pressure is equal to the natural log of our constant times the natural log of E to the negative delta H over RT. Now, when you have natural log times natural log, it comes out to be a plus. So natural log of P is equal to natural log of the beta plus natural log of E to the negative delta H RT over RT. And E and natural log are inverse relationships, so they cancel each other out. So this becomes natural log of P is equal to the natural log of B plus negative delta H over RT. And I'm going to rearrange this a little bit. So we get the natural log of P is equal to a negative delta H over R times 1 over T plus natural log of B. And when you do that, folks, you have taken an exponential function and you have turned it into a linear function that meets the equation y is equal to mx plus b. Don't worry, you're not going to have to do the math, but I want to explain the math. You're going to have to do math, but you're going to have to do it with the equation, not get to the equation.
This is just a lot of symbols.
What we're looking at basically, though, is this as our end result. So in other words, what we can say is the natural log of P is equal to y on the y-axis. Our negative delta H over R is equal to our slope of the line, M. 1 over T is equal to the x-axis. And B would be our, natural log of beta would be our y-intercept. And when you graph this, what you're going to do is you're going to get a linear graph of y is equal to mx plus b. I always forget my directionality. Well, if it's a negative slope, it has to be down. Of that. When you graph natural log of P over 1 over T, you would get a linear line.
So this is what we're practicing the graphing lab.
We will be practicing some of this, and you will also be using some of this later on.
It will always be a negative slope.
In this particular case, yes, because of this value, because it's a negative delta H over R. I brought my book so I'd have problems for it, because that's where I'll be going soon. Now, so let me get to a problem. First of all, before I get into a problem, I do want to explain one other thing, and that is R. R, folks, is another ideal gas constant. But it is a specific ideal gas constant. Because it's the one that deals with energy in specific. So this R is 8.314 joules per mole Kelvin. Okay. Now, there is one more thing. And that is we can go into, we can take the equation that we developed here. And from that equation, we can ultimately get to the Clausius-Clapeyron equation. The Clausius-Clapeyron equation, it works because when we're talking, if you use this equation, you're talking about just one point in time. But with the Clausius-Clapeyron equation, it looks at the change that occurs and what is responsible for that slope. Because remember, slope is the the y minus y over x minus x. So. The Clausius-Clapeyron equation basically, instead of looking at one point in time, deals with 2 points on the graph. And that equation comes out to be the natural log of P2 over P1 is equal to a negative delta H of vaporization over R times 1 over T2 minus 1 over T1. This can be used to figure out the enthalpy for a substance, or it can be used to figure out the new pressure of a substance or the new temperature of a substance due to a change. Yes? Vaporization, VAP.
Looks like we were saying that it looks like
The which one?
is it the Rydberg?
Yes, it does look very much like the Rydberg-Balmer equation.
Yeah.
A lot of similarities.
Do we need to memorize this formula for the exam?
You do not need to memorize formulas or constants for the exam. I will give you formulas and constants on the back sheet. But I'm not going to tell you when to use what. You got to know when to use which one. But I'll at least give you the formula.
So don't memorize the specific equations, memorize
How to use it and what it tells you. That's more important in how to use the equations or when to use what equation and what does it tell you. Okay, so now let me get to a problem. So ethanol has a heat of vaporization of 38.56 kilojoules per mole. And a normal boiling point of 78.4 degrees Celsius. What is the vapor pressure? Of ethanol at 15 degrees Celsius? Going to give a moment for everybody to get this written down.
Does that say 78.4 degrees Celsius?
That says 78.4. My 7 did not look right. How's that? Okay. First things first, I like to do problems so that I can show you the thought process. When I look at a problem to help me, it's the thought process that helps me identify what I'm going to be using and all that jazz. So the first thing I see is delta H of vaporization. So that's the delta H of VAP. And it is told to be 38.56 kilojoules per mole. Now, the next thing I see is something that you need to be prepared to interpret, and that is this term normal. Normal, when we talk about pressure, is either going to be, it's 1 atmosphere's 760 torr, 760 millimeters of mercury. So at this pressure, which we will call pressure 1, you have a temperature 1 equal to 78.4 degrees Celsius. And then it asks you for pressure 2 with a new temperature of 15 degrees Celsius. Now, because I see this delta H of vaporization come into play, that is my clue that I will be using the Clausius-Clapeyron equation. And that means I also need my R value, and the R value is 8.314 joules per mole Kelvin. Now, folks, I know a lot of you did not have me, and I like to use a particular terminology for constants, and that they are dictators. They dictate what your units must be. All units must match the dictator. So your pressure right now is in kilojoules per mole. That won't work. You got to have it in joules per mole. based upon the dictator. So you need to convert that kilojoules into joules. So that is going to be 38,560 joules per mole. The next thing is I see that I am going to be required to have my temperature in Kelvin, not degrees Celsius. So you will need to add 273.15 to your temperatures. So this first one is 351.55 Kelvin. And the second one is 288.15 Kelvin. Now that you have all of your units in the same process, it becomes more of a plug and chug. So the natural log of P2 over 1 atmosphere, or we can use some mercury, it doesn't really matter. They just all need to be the same. Is equal to the negative delta H of vaporization, that is 38,560 joules per mole, divided by our R value of 8.314 joules per mole Kelvin, times 1 over T2, which is 288.15 Kelvin, minus 1 over T1, which is 1 over 351.55 Kelvin. Sorry, I ran out of room. Need to move over some. So right now I'm going to leave the left-hand side the same. The log of P2 over 1 atmosphere is equal to, and I'm going to take care of the left-hand side. When you key it all into the calculator, you get a value of a negative of a negative 2.90. And you'll notice that all the units have canceled. Now, folks, just like multiplication turns into addition for natural log, division turns into subtraction. So this is the natural log of P2 minus the natural log of 1 atmosphere is equal to a negative 2.90. Which log of 1 is 0, so it becomes, it stays the same in this particular case. But now it has the unit of atmospheres. And when you take the inverse of natural log, which is exponential of the negative 2.9, you get a value of 0.055 atmospheres.
Jake, I'm confused on the last two steps. How did you get 0.005 from -2.92?
Okay, so to do so, you would take the opposite of natural log is exponential. So you take e to the power. Well, e of a natural log, those cancel out and you're left with just P2. And e of -2.9 becomes 0.055.
If it was in Tor, would you just multiply the denominator? I did that and I was like, your answer is way different from mine. Oh, you're doing it that. So, right?
Did you change your Tor that you got back to atmospheres?
No, I wasn't, so we did normal. You said that we could use atmosphere for a moment.
Right, the number will come out different, but then when you get to this point, if I wanted to put it in it, I get 41.8 atmospheres, torr. So it all depends upon the unit I want. But it should come out the same answer, just different units. There is a 760 torr in 1 atmosphere, so I multiplied my atmospheres by 760. Other questions? And folks, please ask. Make sure you know what you're doing. Yes. Okay. Okay. So you're asking how I went from this step to this step, or how I went from this step to this step? Okay. So let me just go back. ln of P2 minus ln of 1 atmosphere is equal to -2.90. The ln of 1 is equal to 0. So ln of P2 is -0 is equal to -2.90. So ln of P2 is equal to -2.90. Now, to get rid of the ln, you take the exponential of both sides. So in a sense, we're going exponential of ln of P2 is equal to the exponential of a -2.90. But the thing is, when you take the exponential of a natural log, those cancel out. So that becomes strictly P2 is equal to e to the -2.90. When I plug in e, I use the exponential over here. Now make sure there's, if you look at your calculator, you'll see your natural log button. Directly above it, you'll see an e to the x. For most calculators, you need that e to the x. Other questions? Because I didn't specify whether I wanted it in torr or whether I wanted it in atmospheres, I could accept it in either one.
Oh, okay, so you would specify.
Yes. Yes, it'll be specified which one you want. Or if I don't specify, then it's up to me to look at all the answers.
So then on the our little equation sheet or whatever, will it have that 1 atmosphere is equal to 760? That's just.
You will have that constant too.
So anything that's those sort of constant
Yes. Any constants, any equations besides molarity and molar, that type of thing that you should know. Density I won't give you because those should be part and parcel of the course anymore. But everything else you'll get. You'll get the Clausius-Clapeyron on for certain. And it is our 2-minute break.
You're not gonna give us C1 and B1 and C2.
I am not giving, well, actually, probably not. Some things I will gladly give, other things I'll always go over what I will give. Right, so if you look at a calculator, you can always tell what's in reverse, because natural log has the E button, log has the 10 to the button. Those are inverses of each other.
So log is 10 to the second power.
Correct.
Okay.
Whereas natural log is e to the x.
I got you.
-1 just says it should be in the denominator, so it'll probably have that equal sign.
And I put it on there on another.
Exactly.
Okay. My
So
brain was like,
that it would not have a division sign, it would just have. Yeah.
okay.
I mean, even, well, this combined together comes back to that. I mean, it's still 1/t. I mean, what's delta H is delta H or times T. Or T. So all it is separated from it, to get to the slope in what is the x.
It may just be because it's in the parentheses first separately.
So did I. I made sure I did the 1 minus 288.15 minus 1 divided by the 351.
Right.
And then I I got a.
Do you need to go get a water?
Huh?
Is that what that's for? A
A
water?
Coke.
A Coke. Where's it at?
Oh, don't worry about it. I'll get it after class.
I can get you.
It's
Are
fine.
you sure?
Yes.
Okay.
So 1 divided by 288.15. Whoops. Minus 1 divided by 351.55. And then I get that. I multiply that times a negative 38,560 divided by the 8.314.
Okay, I must have just put it. Thank you.
Not a problem. Okay, folks. It's okay. I'll manage. So let me give you one to work. Slightly different, but very similar.
If you guys live in the store at the other end, are there new machines that are right along?
They're looking for you with my own.
Okay, let's see how you're doing. So first thing I did is you'll notice every time I work a problem, the first thing I do is basically take all the words and get it down to all of the components of the equation. So that's exactly what I did. I got the delta H in there and P1, T1, P2, T2, and it told me that I was going to be using Clausius-Clapeyron equation from that information. So I identified the equation from the information. Then I realized I needed the R value, so I added the R. But basically, the R dictated what the unit for the enthalpy needed to be. So I changed the enthalpy over to 30,720 joules per mole. And I changed the temperature because, again, R was dictating it needed to be in Kelvin to 353.25 Kelvin. And the other thing, though, that I did is I noticed that the second pressure I was given was in torr. So I made sure that when I started putting it into the equation, I was using matching units. So then I entered everything into the equation. And taking the left-hand side, that comes out to be a negative 0.535 is equal to this negative 30,720 joules per mole divided by 8.314 joules per mole Kelvin times 1 over T2, whoops, minus the 1 over 353.25. Then I multiplied by 8.314 divided by a negative 30,720, and I got I got 1.449 times 10 to the minus 4 is equal to 1 over T2 minus 1 over the 353.25 Kelvin. I then added 1 over 353.25 Kelvin to both sides. And I got 1 over T2 is equal to a 0.002976. And now what I would do is I would use my inverse button, which is x to the minus 1 on that number. And it gives me a value of T2 equals 336.05 Kelvin. Yes.
When you started doing the left side, the very first part, with the 4.5 or 764, how did you get the negative 0.535?
So you can do the 445 divided by 760, but basically what I did is I took the natural log. And when you key in the natural log, it automatically opens up a parentheses. I did the 445 divided by 760, close parentheses, and hit enter.
How did you get the 1.449?
So to get that, so let me do it this way. To go here to here, I multiplied by 8.314, and I divided by a negative 30,720. And I did that. I mean, technically, the other way you could have done it, folks, is you could have solved this first and gotten a value and then divided the negative 0.535 by whatever that answer is. Both ways work. Other questions? And then to go from the next step, I added 1 divided by the 3, 53.25 to get to 1 over T2. So folks, let's just, I want to take a moment to explain what this means. Because understanding it is part of what I want you to know is, I mean, it's great to be able to do the math, but do you know what the math means? That's one of the reasons I love chemistry, is because it's applied mathematics. And so that application means something. So what does it mean? It means that if benzene is at 1 atmosphere, then its boiling point is 80.1 degrees Celsius. But if I alter the pressure to 445 torr, then then benzene will boil at 62.9 degrees Celsius. Folks, this is exactly what goes on when you're traveling locations. When you go, for instance, from here to the Mile High City, you're changing the pressure. You're going to change the temperature at which things boil, because there's a difference in pressure. Now, I'm not saying it's going to be as dramatic as this example, but that doesn't matter. That's what's occurring. So, questions?
So this is the kind of problem that you could apply to like making eggs or baking brownies in the mountains versus at sea level.
Yes, they're going to cook a lot faster in many cases because it takes less time to get it up to that temperature. Okay, so I'm going to introduce the next topic, but we won't get into the next topic until tomorrow, till Wednesday, as far as actually working some problems associated with it. And that is, we're going to talk about heating and cooling of substances. I mean, we've already been talking about it, but we need to go into a little bit more detail. Okay. So we know that there are 3 states of matter. You have a solid, you have a liquid, and you have a gas. To go from a solid to a liquid, we've always called that melting. So this process is related to the melting point. To go from a solid to a liquid, you must add in energy. Must add energy to make that happen. Because as you go from a solid to a liquid, what are you doing? You are causing some of those intermolecular forces to break apart. So you got to add some energy to make that happen. Then as we go from a liquid to a gas, that is considered to be evaporation. And it does occur around our boiling point. Again, folks, you must add energy to this. And in fact, you must add quite a bit of energy to this, because now you must overcome all of the intermolecular forces. Now, the reverse of this process is called condensation. If I can spell, it would be good. And it's going to have a negative delta H that's equivalent to the positive delta H for evaporation, just opposite in sign. And to go from a liquid down to a solid, you're going to have freezing or solidification. And again, this is going to be a negative delta H. It's going to be the same amount of energy, but it's going to be given off instead of absorbed. Now we do have also, we can go from a solid to a gas. If we want to go from a solid directly to a gas, this is called sublimation, which is what dry ice does. This process is a positive delta H. And the reverse of that is called deposition with a negative delta H. Now, the neat thing about sublimation's delta H of sublimation, that is going to be equal to the delta H of melting plus the delta H of evaporation. For the sublimation, the enthalpy of sublimation is equivalent to the enthalpy of melting plus the enthalpy of vaporization. Because, folks, if you're going to sublime something, you got to overcome all of the forces all at one time. So you got to add them all together. We are going to be using this information when we start dealing with what are called heating and cooling curves. This would be a heating curve that I'm about to show you. We start out in the solid phase. We go through what's called the delta H of fusion, which basically, folks, this is that melting, and it occurs at the melting point. And it takes a while because it's not all in one phase. Then you have your liquid phase. And then you go through your delta H of vaporization. And again, it's a flat line because you're going to have some molecules going into vapor form as quickly as others go back into liquid form until you can overcome all of the forces at once. And the delta H of vaporization occurs at the boiling point. And then you finally get into the gas form. There are different equations we will use to calculate how much energy is associated with each of these five. Said the word five. Each of these 5 stages. And that is where we will pick up on Wednesday, is we'll get into the calculations associated with each of those 5 stages. 3 of them, the liquid, solid, and gas, you actually already know. That's Q is equal to MCAT. We'll just have to talk about the delta H of fusion and delta H of vaporization. And then combine them all. Fusion, FUS, or is what its symbol is FUS, fusion.
Sorry for having to like run out like.
Not a problem, I do understand. Trying to make sure everybody has chance to finish. Huh? Yeah,
How did you get them this?
I use the inverse on your calculator, that button. But you can also, I mean, I can do it the long way if you need algebraically, but if you'll remember that means anytime you have a 1/over, hit that button and it automatically will do the calculation for you.
So, Dr. Yarber. is it
Yes.
Normal for this to feel very. It's like that heating curve we found is in physics.
Well, I mean, yeah,
I know it's
there's a
different.
lot of, yes.
I'm trying to figure out if I can use my physics brain.
Yes, you can use some of your physics brain for this.
Okay.
It is,
It's like the
there's
math.
relationships.
The math is like that physics is where you gotta get it.
Chemistry and physics and have a lot in common. We tend to focus more on the molecule itself, but we use a lot of the same applications.
Right.
We
Okay.
just have different, the biggest issue is I know from my experience with physics, we have different notations.
Yeah, the symbols
sometimes.
are all different.
But
Luckily, I'm not in
concepts are
physics. Right.
similar.
Thanks.
I know online you said you guys at your office hours, but are you going to be in it after this, or do you want?
I am going to my office now, yes, for a few minutes.
Chat for like 5.
Sure. Let me get it all logged out.
Okay.